In order to study how action potentials are generated, we will first insert two electrodes into the neuron, one to record the membrane voltage and another to inject current that can be used to push the membrane voltage toward more positive or depolarizing, or more negative or hyperpolarizing voltages. Let's look at what happens when our model neuron is stimulated. The first two stimuli shown here are insufficient to depolarize the membrane past the threshold level. Thus, no action potential is generated and the voltage quickly returns to the resting level. However, the final stimulus is large enough to generate an action potential. In this experiment, the current injected into the cell, the stimulus, is represented in the upper graph, and the voltage response below. Notice that a hyperpolarizing current drives the membrane potential in a negative direction, with the voltage response of the cell directly proportional to the magnitude of the injected current. The same relationship is true for small injections of depolarizing current. The voltage response of the cell is directly proportional to the magnitude of the injected current. If the stimulus is sufficient to push the membrane potential past the firing threshold for the neuron, such as the second stimulus in this example, then an action potential is generated. Depolarization of the membrane past threshold sets in motion changes in membrane conductances that eventually leads to generation of the action potential. Note that the action potential is an all or none event. Once generated, its amplitude does not vary as a function of the size of the preceding stimulus. Any suprathreshold stimulus will produce an action potential of similar amplitude and duration. The action potential can be divided into 6 phases: an initial steady state or resting phase, a rising phase, the overshoot phase, the falling phase, the undershoot phase, and the recovery phase. We'll now examine each of these phases in turn. When a neuron is at rest, only the so-called leak potassium channels are open, establishing the resting potential. These potassium channels, a subset of all potassium channels, are constantly in the open state. During the rising phase, the increasing positive shift in membrane potential is driven by the opening of progressively more and more voltage-gated sodium channels and the entry of sodium ions into the neuron. This inward sodium current depolarizes the membrane voltage, as indicated by the red color shift in the membrane. The membrane potential is now at its most positive state. It is overshot 0 millivolts. At this positive potential, two processes are occurring simultaneously. First, the voltage-gated sodium channels that initially activated during the rising phase begin to close. As a result, sodium conductance starts to decline. Next, potassium channels begin to open, driving the membrane potential back toward the equilibrium potential for potassium. These voltage-gated potassium channels differ from leak potassium channels in that they are normally closed at the resting potential but open in response to depolarization, thus the term voltage-gated. Now, the action potential is in its repolarizing phase, i.e., the membrane potential is rapidly returning to the resting potential. During the falling phase, activation of voltage-gated potassium channels is at maximum, and the number of open sodium channels is dramatically reduced. At this stage, the action potential repolarizes beyond the resting membrane voltage. This hyperpolarization is indicated by the blue color of the membrane. The undershoot occurs because most voltage-gated potassium channels are still open, such that the total potassium conductance of the neuron is greater than when the membrane is at its resting steady state. During the recovery phase, the membrane potential returns to the original steady-state resting potential. This occurs as the delayed potassium channels that were open during the action potential now close. The membrane potential is now determined by the other channels normally open at the resting potential. In fact, the transition between the phases of the action potential is seamless, and one stage grades smoothly into the next.
This circuit contains a resistor, a switch, an open spot in the wire, and a battery that supplies a voltage potential V sub B. When we close the switch, no current flows. If we reopen the switch, install a parallel plate capacitor where the break was, and then close the switch again, the current jumps to a value V sub B over R and then gradually declines to 0. The charge Q on the upper plate of the capacitor, which is the integral over time of the current, rises from 0 to a final value Q final. Meanwhile, the voltage V across the capacitor rises from 0 to a final value V sub B. Notice that the graph of charge versus time has the same shape as the graph of voltage versus time.
Oh, that's just perfect.
Ohm's law is one of the most basic principles in electronics, yet it is not an actual physical law. Understanding Ohm's law is critical to understanding how electric circuits work. Understanding why it is not an actual physical law is critical to understanding the basic principles of logic and the nature of physical laws. Suppose we have a battery and a device which we call a resistor. The battery will create a voltage, causing charged particles to flow around the loop. On the other hand, the resistor tries to prevent the charged particles from flowing. The number of charged particles that pass by each second is what we refer to as the current. There are 3 ways to increase the current. The first way to increase the current is to use more batteries to create a larger voltage. The second way to increase the current is to use a resistor with a smaller resistance. The third way to increase the current is to use several resistors in parallel. Having several resistors in parallel is the same as having one resistor with a much smaller resistance. On the other hand, having several resistors in series is the same thing as having one resistor with a much larger resistance. Let us create a precise mathematical definition for the word resistance. Suppose we take the voltage across the resistor and divide it by the current passing through it. The result of this division is what we will define as the resistance. This is what we refer to as Ohm's law. However, this is not really a physical law, but simply the arbitrary definition that we created for the word resistance. Physical laws tell us how the universe works. Ohm's law would tell us how the universe works if, for example, the value for the resistance of a material always stayed constant. However, this is not the case. As current passes through a material, the material heats up. As a material's temperature changes, its resistance also changes. With most resistors, this effect is relatively small. In the case of some resistors, this effect can be very large. If this effect is large, we can use it to our advantage by using the resistor as a temperature sensor. By placing a voltage with a known value across the resistor and measuring the current that passes through it, we can calculate the resistance of the resistor. This would give us information about the resistor's temperature, and therefore also give us information about the temperature of the material that the resistor is in contact with. Temperature is just one of the many factors that can cause the resistance of a material to change. However, when we say that the resistance changes, all this means is that if we take the voltage across a resistor and divide it by the current passing through the resistor, we will not necessarily always get the same number. The fact that the number that we get at any given time is always equal to the resistance of the material is simply due to the fact that this is how we defined the word resistance in the first place. There are many examples in logic where a statement is always true simply because of the way in which we created our definitions for the words. And the statement doesn't actually tell us anything about the external world around us. This is one of the logical fallacies we need to watch out for, both with regards to science and also with regards to life in general.
I'm ready, 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 ready.